right, chapter 5, we're getting into integration. Just like with differentiation, we had partial differentiation. We're going to do partial integration. We don't really call it that, but that's basically what it is. So here's how it's going to work. Here I've got a double integral, and I've got my dy first, and then a dx. So the way I'm going to evaluate that is I'm going to pull out the inside integral, number it, and you have to do this, number it with the number 1, and that's my first integral, and I'm going to integrate. Now, since I'm integrating with respect to y, I'm holding x constant. So if I hold x constant, integrate y, I get 1/2 y squared. So this is x y squared plus, remember, x is a constant, so the integral of a constant with respect to y is that constant times y. So xy, and I'm going to evaluate that between 0 and 4. And you're plugging 0 and 4 in for y, not x. Okay, so that gives me 16x plus 4x. And then when I put in 0, I get everything is 0. So I get 20x. That's the result of the first integral. Then I do the second integral, and I number it with number 2. And I use the limits on the outside integral here. They go from 1 to 2. I use the answer from my first integral, which is 20x, and then I'm integrating with respect to x. Now I'm going to get a number when I integrate. So that's going to be 10x squared between 2 and 1, which is 10 times 4 minus 1, which is 30. That's how you evaluate a double integral. Now, there's a theorem called Fubini's theorem, I think I put it on the last page of the lecture notes, that says you can change the order of integration here. You can go dx first and then dy, and that's what I've done here. Dx goes first and then dy, but when you do that, you need to change the limits so they correspond to the variable. So the y limits go from 0 to 4. Those were first upstairs. Here, they go over here because they have to match the dy. And the 1 to 2 are the limits for the x variable, so they have to match the dx. Notation method 2, you're not allowed to use, but I do want to mention it because the videos, I love Sousa, as you know, I really love him, but I don't like the fact that he does his double integrals using method 2 because students have a really hard time using method 2, which is to carry along the outside integral the whole way as you're doing the inside integral. Now, for a simple integral like this, it's not bad, but when you're doing integration by parts and u substitution, it gets to be a nightmare. So you cannot use this method. I won't let you do it. You won't get any credit on a test or your lecture notes if you're using that method. You're going to have to number your integrals, pull the inside one out, evaluate it, and then do the second one. Okay, so let's do an example. We're going to integrate this function over the region R, and R is this rectangle. X goes from 0 to 1, y goes from 0 to 2. So I'm going to do dy and then dx. That means when I put my limits on, xy cubed x squared plus 1 dy dx. The first limits on the inside integral have to be the y limits, and that's 0 to 2. And then the x limits, those go on the outside, that's 0 to 1. And so I could switch those limits. I could go 0 to 2 and then 0 to 1, but then I'd have to go dx dy. Get the same answer in the end, but I'm going to do it this first way. So using the numbering system, number 1, we're going to pull out the inside integral, 0 to 2 xy cubed over x squared plus 1 dy. Now x is a constant, so we're just integrating y cubed, and all this other stuff just carries along. So this is going to be x over x squared plus 1. That's all constant. And then when I integrate y cubed, I get 1/4 y to the 4th. And I'm going to evaluate that between 0 and 2. So that's 4x over x squared plus 1. Integral 2, I use the outside limits, 0 to 1. I use my answer from the first integral and dx. Okay, so this is going to be a u sub. I'm going to let u equal x squared plus 1 du is 2x dx. 2 du would be 4x dx. So this is going to be twice the integral of 1 over u du. And I'll change my limits. When x is 0, u is 1. And when x is 1, u is 2. So that gives me 2 ln absolute u between 1 and 2, which is 2 ln 2 minus 2 ln 1, but ln 1 is 0, so 2 ln 2 is my answer. Okay, so let's look at some applications. When you integrate the function 1 dA, and dA is dy dx or dx dy, you get the area of the region you're integrating over. And so in the next section, that will be pretty interesting, because in this section, we're integrating over rectangular regions, which is kind of boring. But in the next section, we'll be integrating over curvy regions, and we'll be able to compute the area of this region by just doing the double integral dy dx or dx dy. For volume, a double integral can be interpreted as volume. If you integrate a function z equals f of xy, you're going to get the volume underneath that surface over the region that you're integrating over. And then there's an average value interpretation also. And I want to show you these and compare to the results we had from earlier calculus classes. Remember how it worked for area. If we had one curve f of x, the area underneath the curve f was found by integrating a to b f dx. If you had two curves, you did f minus g from a to b dx. Same thing with volume. If you've got one surface, suppose this is your z equals f of xy, and you want the volume of this shape here, the volume is going to be the double integral over the region R of f of xy dA, where dA is dx dy or dy dx. Now, later on, when we have two surfaces, like an f and a g, if you want the volume of the solid bound by f and g, then you're going to integrate, double integral over R, and you'll do f minus g dA. And then average value, I don't know if you remember the formula for average value of a function over an interval from a to b, but what we did is we integrated f from a to b, and then we divided by the length of the interval. And we're going to do something similar in two variables. We're going to integrate f, but we're going to divide out by the area of the region we're integrating over instead of the length of an interval. And so the geometric interpretation, f average here is like the average height of this curve. Same thing over here, f ab is going to be the average z value, average height of this surface. Okay, so let's do another one. Suppose R is the rectangle given by x goes from -1 to 1, y goes from 0 to pi, and consider this double integral. Write down two iterated integrals. Iterated integrals are just double integrals with the limits on them that you could use to find whatever this number is. Which one would you evaluate if you actually had to do it? So we're going to go x, y, cos y. Our options are dx dy or dy dx. Now the limits, if we go x first, we need to put the x limits on the inside and then the y limits. If we go y first, we got to put the y limits on the inside, 0 to pi, -1 to 1, the x limits go on the outside. So Fubini's theorem tells us these are going to be equal, but sometimes one integration is going to be easier than the other. If I had to do this, I would not do the second one, because if I do y first, to integrate y cos y, that's going to be parts, integration by parts. Whereas if I go x first, integrating x is easy. It's just going to be 1/2 x squared, and then something good's going to happen. So you're going to do this for homework. You're going to show that this is actually equal to 0 when you do the integral. I'm going to do one more problem with you. Evaluate this double integral, and you've got one like this in your homework. So first we do the inside. 1, pull out the inside integral, 0 to 2, x e to the x plus 5y dy. Now x is constant, So this is actually just, you can all do this by inspection. This is going to be x over 5, or 1/5 x e to the x plus 5y. Okay, and then our limits are 0 to 2. So that's 1/5 x, and then when I put 2 in, I get e to the x plus 10, and then when I put 0 in, I get e to the x. Okay, so integral 2 goes from 0 to 1, and I use my answer from integral 1, dx. This is going to be parts. So I'm going to let u equal 1/5 x, du is 1/5 dx. I'm going to let dv be everything else, e to the x plus 10 minus e to the x dx. So v, when I integrate, I just get the same thing, e to the x plus 10 minus e to the x. So when I do integration by parts on a definite integral, first I do the indefinite integral. Then I get my answer, and at the bitter end, I put in the limits. Okay, so this is going to be uv minus the integral of v du. So 1/5 x e to the x plus 10 minus e to the x minus the integral of v du. I'll put my 1/5 out here, and then e to the x plus 10 minus e to the x dx. So that's 1/5, I'm just copying down this first part, x, e to the x plus 10 minus e to the x. And then I'm going to integrate and distribute the minus 1/5 at the same time. The integral of e to the x plus 10 is just e to the x plus 10. So that's minus 1/5 e to the x plus 10. And then plus 1/5 e to the x. All right, now to get the definite integral, 0 to 1, of 1/5 x e to the x plus 10 minus e to the x dx, I just take this whole answer here and plug it in between my two limits. So I'm going to take 1/5 x e to the x plus 10 minus e to the x minus 1/5 e to the x plus 10 plus 1/5 e to the x. It's a lot of writing, between 0 and 1. All right, so let's see what happens. Okay, when I put in 1, I get 1/5 e to the 11 minus e to the 1, which is just minus e, and then I get minus 1/5 e to the 11 plus 1/5 e to the 1. And then when I put in 0, this part gets all canceled out because x is 0. So but this part doesn't. I'll get negative 1/5 e to the 10 plus 1/5. Okay, so now that's 1/5. A lot of stuff's going to cancel. 1/5 e to the 11 minus 1/5 e minus 1/5 e to the 11 plus 1/5 e. Actually, kill. So I'm getting nothing from that first part. And then I get a minus, which is a plus 1/5 e to the 10 minus 1/5. So that's my answer. 1/5 e to the 10 minus 1/5. Okay, so kind of long, but not so bad. In the next section, we'll ramp it up and we'll integrate over more complex regions than rectangles.